Welcome everyone. Today we're going to talk about possibly the smallest type of systems at this conference. We had a lot of talks about huge language models and other big machine learning. We'll talk about some of the smallest that is applied out in the industry. My name is Jon. I work as the head of data science at Sound Sensing. We use sound vibration analysis on sensors to analyze ventilation systems, HVAC, for commercial buildings, so building typically like this. And we notice when something is weird, odd, anomalous in these systems and give the operators an alarm that they can follow. Today we'll talk about machine learning on microcontrollers, sometimes called TinyML. We'll cover that a bit in general. We'll talk about the EMLearn project, which I maintain, and we'll show some real live projects made with EMLearn, and we'll do a quick how-to. How would you get started using this library and doing such an application? And as a bonus, we might go a bit more technical, a bit deeper into model optimization, if we have time. So first, who here has any background with, let's say, hardware, microcontrollers, electronics, Arduino related? Okay, quite a lot of hands. That's great. If you don't, you should also find this relevant for you. You will get some intro. So what do we use machine learning for when we talk about these kind of systems? The most common by far is to do some automated sensor data analysis directly on a sensor node on a device. So such a system can be described roughly like this. We have a set of sensors, could be one, could be multiple. They typically have a relatively high data rate. They're what you could maybe call like unstructured data. Cameras, microphone, accelerometer for motion, or any like custom sensors, radar, lots of options, lots of great sensors that are very affordable now and very powerful. But the information that we're interested in is usually not the raw data. We want to extract some information. So we can do that directly on a microcontroller that's connected to the sensors. And when we're doing machine learning here, we're talking about we do a training on our computer or in the server, and we'll have a deployed, trained model in the microcontroller. So we do inference on these devices. And typically there's a little bit of pre-processing and post-processing involved as well. And then on the system, you might then transmit the extracted information, a low bit rate of data over wireless communication, wired, maybe even some legacy protocols that can't handle a lot of data, or you maybe act on this directly by controlling some motors, etc. And the benefits of doing this versus sending the data to the cloud and doing kind of all the inference and machine learning and data processing there is that you can build systems that are standalone, that are low latency and guaranteed latency, and that are highly power efficient, that can respect privacy because we do not need to send a potentially sensitive data stream onto the cloud, and you can make things very low cost, which enables usually massive scale in terms of the number of units you can deploy, which is relevant in many scenarios. So some applications of this, in consumer technology, if you do some what's called keyword spotting, so detecting, hey Google, hey Siri, etc., to start like talking to your large language model, that very often or almost always runs on a dedicated microcontroller in these type of devices, be it this kind of home style device or being in a smartwatch or on your phone. So that's a very like established task of keyword spotting. Also in consumer tech, if you have a fitness tracker or maybe sleep quality tracker, etc., that will run some simple machine learning models directly on your watch, typically. And in industrial settings, there's many applications. At Sound Sensing, we monitor machinery, but there's also things for animal monitoring and many other cases. But this is also quite a accessible area, so you could just do things for fun. So you can make magic wand. Instead of having buttons to control things in your home, you can have a magic wand. You make a gesture to control whatever you want. Or you could make a smart doorbell that lets in your cat, or a cat, as long as it's your cat and it does not bring any unwanted gifts to you. And you can let it in automatically. And otherwise it has to stay out. And anything else you could imagine. So what are microcontrollers? That's where we will deploy our software. They are tiny programmable chips. And this spans a huge range of processing power, but all of it in a quite small domain. So you might have up to 1 megabyte of RAM, 10 megabyte of program storage, and prices might be from 10 cents to $10 for the chip. And you can build complete sensor units, including battery power, wireless connectivity, whatever you need, for under $10. And microcontrollers are maybe not something everyone is directly exposed to, but they are everywhere. So in a car, a typical modern car has now over 80 microcontrollers in all the different subsystems that are talking to each other. And all electronics you have in your home have one or more microcontrollers. And it's become increasingly accessible for hobbyists or like non-specialists in this area. There was the Arduino project from very early on. Something called ESP32 was released, has Wi-Fi and lots of nice things like that. And now from Raspberry Pi, for example, they do a lot of beginner-friendly, non-specialist-friendly things, really nice chips. And there's also something called MicroPython. If you don't program so much in C, you can now do Python on these type of devices. I'll cover a little bit about that today. So what is EMLearn? It's an open source project that I started to do machine learning on these type of devices, or for these type of devices. It's composed of 2 parts, which reflects the stages of this type of development. There's training tools. So how it will work, you train your models in very much the standard way, any machine learning project, using a standard library such as scikit-learn, keras, etc. And then EMLearn provides a one-liner to export this into an optimized C model or optimized model that can go on device, and including some validation tools, because we're doing conversion and you want to make sure that your model is still correct. And then there is the other side that gets deployed onto the device. There are 2 options. There is a C library, which is the low-level kind of core, and that is portable C99 code, embedded friendly, no dynamic allocation, etc. So keeping a professional standard on that. And it can be used on any platform that can run C, which is basically any platform in these kind of environments. And there's some small, simple integrations with Zephyr, Arduino, etc. that just make it extra easy to use on those common platforms. But there's another alternative, which is EMLearn MicroPython. And that's for MicroPython. And that makes it super convenient if you are not a C developer to get started. So we support the typical tasks for these type of devices, which are anomaly detection, detecting something is odd or unusual compared to normal data, classification, which is giving a discrete class out, or regression tasks, which is sometimes also used to make a sensor that gives a simple reading out, but you might have used something advanced as the input, like radar data. The model we support, it's mostly around what we call classic ML, but we do have support for simple neural networks, multi-layer perceptrons, and convolutional neural networks. But we focus on really the smallest systems, because this is very often sufficient and much easier to use on these type of devices. So here's some real-world projects. So it's been referred to in at least 40 academic publications, probably used in many more projects, but you don't always hear about the consumers in open source project. But here's one example. This was made by a student at Virginia Tech, although I know that related tech is now deployed on industrial scale. So it's for tracking of milk cows or their health. So it uses a model that runs directly on this device with the accelerometer. So it's used to classify the behavior of the cow based on the motion into lying, grazing, standing, ruminating. And then that is compared to what is typical for a cow during a day. And if that drifts considerably, you might have a situation that needs looking into. Maybe your cow is lying way too much. That could be a bad sign. Or it never relaxes at all. It could be chased around or stressed. So that's one example. And Samsung Research did a project for personal health, especially for people that have respiratory health problems, to help monitor that in every day to see maybe what are the triggers. This is difficult to understand if you cannot track in the everyday scenario. If you can only track it in the lab, it can be hard to figure out. So they made a model that combines actually two data streams, both the audio as well as the motion from the accelerometer, that both do this kind of estimation of your breathing rate. And they found that when you do both of these in this kind of in-ear headphone, they could get reasonable accuracy and power consumption for this use case. Here's a project I did, mostly for fun. It's a automated toothbrush timer. So you have to, it will track how long you're actively brushing your teeth. So you only get kind of points when you're actually brushing, so that you reach your recommended 2-minute, which you're supposed to do every day or every time you brush your teeth. And this is completely open, of course, so it's a great also starting point for related applications. And here's another research project that I do, and looking at what really are the limits, like how small can we go, or not physically small, but how simple can we do things that are still a usable system. And I was able to put together a complete system, including a power solution and wireless that is under $1 in total bill of materials. So this is kind of where we're going. This might be like a little bit stretching it, but in the future we're definitely going here. Like this is doing this kind of machine learning on these kind of devices is almost for free, in the sense that you usually have capacity to spare on the microcontroller you need anyway for the process. So yeah, this is where the things are going. So I'll show you quickly the C library, how you would use that. So as I mentioned, you would train using your standard machine learning tools, your standard pipelines. Here's just a snippet showing a piece of the training with the Keras. There's, of course, a data loading loop and all the usual stuff around it. Once you have a trained model that you're satisfied with in terms of performance, etc., then you use the emlearn.convert function and the save function of that. And that will then output a generated C header file, which you can then later include in your project. So this is an example from a simple neural network, and it's similar for the other type of models. So on the device side, or in the firmware side, you include the generated header file that then has kind of everything that you need in there. And you need to read your sensor data. You do that however is usual on the platform that you have. You might have some pre-processing, or maybe it doesn't require so much pre-processing, but then you will have some features that will go into your model. And then you can do something with this data also using your standard platform, if it's Arduino or Zephyr or others. So that's one example. This is like the low level and the most power efficient, of course, and also space efficient. But if you're not used to embedded programming, I would suggest maybe starting with MicroPython. So the motivation for supporting MicroPython in emlearn is that Python is the lingua franca for machine learning. So you can basically almost always expect a machine learning engineer or someone that's exposure to that to know Python, but not necessarily know C. So how can we enable people to build these kind of tiny ML devices using Python? And that's made possible using MicroPython, because that it's been available for around 10 years now, so it's getting actually really nice and mature. And it's as compatible with C Python, like regular Python, as possible, but of course there are constraints when you have these very small devices. So for example, the C API is not compatible. So it means you don't get regular NumPy, TensorFlow, etc. And probably even if the API was compatible, it wouldn't work, because those libraries, they will spend way much than 1 megabyte of RAM just loading them. So what we need is some tools that can replace and be compatible with that. One super cool thing with MicroPython is it has a package manager, which can of course install Python packages onto your device, but it can also install C modules at runtime, and this is very unique in the embedded space. So emlearn then provides a MicroPython library, actually a set of independent modules, which are implemented in C, but provide a convenient Python interface. So as an application developer, you just deal with Python, but it's very efficient, both in terms of space and execution time. So they're distributed as individual modules in this .mpy format. So there's like a one-liner to install that onto your device. And it's considerably faster than if you would do that code in plain Python on the device, which really matters here on these constrained devices. There's a little bit of support for on-device learning for some methods, and we might extend that a bit in the future. So using that is quite conceptually very similar to in C, but you now just a little bit more convenience to import the library. Use on the PC side it looks basically the same, but we support storing to a loadable format like CSV in the case of trees. You can then copy that file over to your device at runtime, so you don't need to reflash and things like that. It's nice, quite convenient. And then here's how you would install that, the C module that enables the classifiers to run. So loading is also quite similar. Here you construct a model, or like the skeleton for a model, and then you can load the model weights or the model coefficients on the device. And you can load it from file system. MicroPython comes with a file system, which is also very convenient, for example, when you want to do data collection or data validation, like run from a file that you know and test your model on device. And in MicroPython, you would also read and do some pre-processing and then do prediction to run your inference, and then do something with it, trigger a motor or send it over Bluetooth, low energy, etc. There is quite a large set of examples, or very realistic examples provided in emlearn MicroPython. So there is this kind of activity tracker or fitness tracker type thing where there's also data recording tools, so you can easily do it for your own custom application, be it like for yourself, for a human, or for a pet, or whatever. There's some audio example, and there is some image classification example. So and those are actually good starting points. Even if you're interested in C, you could kind of see the overall workflow. There's some tools there that are also relevant for C. So that's the core part. So as a summary, we've learned that machine learning is used in embedded systems to automatically analyze sensor data, and that you can do practical applications, like the examples that we've shown, with just a few kilobytes of RAM and a few milliwatt of power, and for a couple of dollars per unit. And emlearn is an open source project that helps you deploy machine learning models to microcontrollers, running either with C or with MicroPython. There's a bunch of documentation separated for these two libraries, and I've also given more like in-depth or focus talks at different conferences, which you will also find linked from the documentation. So that's everything I had. Thank you. Yeah, and we have 5 minutes for questions. So yeah, we got one there.
I have 2 questions. They're kind of related. I'm wondering, like, is it even a thing to have like single instruction multiple data, parallelization on this small device, like chips?
Yes.
That's one. And then whether you support that. So
Yes. Yeah, so the question is it relevant with single instruction multiple data SIMD on these type of devices? Oh. And whether this library supports that. Yes, it is quite relevant. ARM Cortex M4 is quite established, like almost 10-year-old microcontroller now, very typical to use. That has an okay instruction set for SIMD, so it's like usually you can do 8-bit 4 at a time, and that's quite useful. We don't support that directly in the library because we focus on the smaller neural networks, etc. But there is, for example, ARM SimSys NN for neural network that has like support for these accelerators that are then specific to that. And the similar, like new microcontrollers coming out do often have some sort of DSP SIMD type instruction set that can help. And nowadays we're even moving to the stage where there's a lot of NPUs, like microcontroller grade NPUs, super low power, that are kind of attached to your device. So that's coming out in the next, year, 5 years. We're going to see much more of that. Yes. Any more questions there? Yes, which kind of sensor do we support? So since the library expects you to provide the data coming in, you could use it for any sensor. We have then these examples that are very relevant for accelerometer/gyro for motion or vibration, etc. Microphone for audio is very common, and there's example also for camera for images or like low resolution, low frame rate video. And I know that other people have used it with radar, this kind of time of flight, potentially LiDAR, etc. So you can plug in anything you want there. Yeah. Yes, great. That's a good point. Any more questions? Yes, there.
Possible to move the weights to a separate EEPROM, or is everything in the flash?
Yeah, is it possible to move the weights to a separate storage or EEPROM? Yes, you can. You're essentially you can do that. So on the C library, when you generate the code, that's designed to go into program storage, just static. And most compilers will like have a special annotation that says like, oh, put it in that reserved place. And there's when you do the convert, you can specify, add these annotations so that it does the right thing. And if that doesn't do it, I think you could probably do it manually. So yeah, there's some support for that. More questions? Here?
Yeah, thanks. It was an interesting talk. You gave one example of like doing image recognition on your cat and then image recognition of like carrying an object. That seems to me like quite a large model that would be needed for that. Is that not too large for microcontrollers? And at what stage would you be like, okay, this task is too big for a microcontroller, we'll just do it kind of standardly?
Yep.
And is that example in the limit of what's acceptable for a microcontroller?
Yes. The question is, there was one example shown with more like object detection of a cat. Is that doable on the microcontroller grade, or where does typically become a limit to where you want to go to a bigger system? So yeah, you can. So I think like the smart doorbell, you probably don't need object recognition. You could probably just, if you position it well, you design it well, like you have a cat hatch or something, you could just do all the image classification. That would work super well. You don't need high frame rate or super high resolution to recognize a cat. But an object detection is like it's not on the upper edge. But microcontrollers, some of them are now pushing like 600 megahertz clock speeds with like into dual core, and where you can even have SD RAM on it, so like 100 megabytes of RAM. So yeah, you can do actually quite a lot of, if you go with the higher end, you can do quite a lot of computer vision. And there's projects like OpenMV, which really focuses on like that exact area, and they provide tools there. But of course, if you don't have a good reason to go for a microcontroller, if you're in that area, it might be just easier to do it on a Raspberry Pi, small embedded Linux type system. So it's like, it's mostly relevant. You can do it, but you should only do it if you need that power constraint, or you need the cost per device to be, quite low. Otherwise, for image stuff, I would definitely consider going to a embedded Linux type device or phone if that can fit your use case.